Hi everyone. In this video, we're going to continue the conversation about inverse functions. In the previous video, I mentioned that in order to anti-differentiate rational functions, we need to know how to anti-differentiate partial fractions. And for that, we need to study inverse exponential and trigonometric functions. So let's start with the exponential functions, beginning with this definition. An exponential function is defined as a function of the form y equals a to the x, where a is a positive constant. So here's a typical example of an exponential function. 2 to the x would represent multiplying 2 by itself over and over again, where x is the number of times it gets multiplied. And each time we multiply by 2, the result gets larger, which is why we have an increasing function here. And the same can be said when we multiply repeatedly by any value which is larger than 1. So in those situations where the value of a is larger than 1, we get what's called exponential growth. On the other hand, if we were multiplying by an a value which is less than 1, such as a half, the result would get smaller each time we multiply, resulting in a decreasing function. And so these situations where a is less than 1 are what we call exponential decay. There's also the case where a is equal to 1, but in that case our graph would neither increase nor decrease. It's important that you be aware of what these graphs look like, especially later on in the course when we start calculating limits, since these graphs reveal to us the behavior of an exponential function, for example, when x is approaching infinity or minus infinity. So make sure to commit these graphs to memory or at least have them on a formula sheet at bare minimum. What you'll notice about exponential growth and decay functions is that they pass the horizontal line test, and so an inverse function can be considered. There's a name for the inverse of an exponential function. That's what we call a logarithm. In fact, that's the definition of what a logarithm is. The logarithm with base a is defined as the inverse of the function y equals a to the x. Let's think about what that means. We know that inverse functions are supposed to cancel each other out or undo each other, to put it another way. So let's say we started with some value of x. And to that x, let's say we applied a base a exponential to form a to the power of x. If we were to then apply the base a logarithm to that result, the outcome of all that must just be x according to the way inverse functions operate, because anytime we apply inverse functions in succession like this, what returns to us must always be the x that we started with. It's common to informally think of this as a cancellation between a and log base a. And the same should be true if we applied these functions in the opposite order. So if you started by taking your x and applying the log base a, and then applied the base a exponential to that result, the outcome of this should again just be the x that you started with. And again, we can informally think of this as a canceling with log base a. Now, I have no doubt that you've seen these formulas before. They're often called cancellation laws. But depending on how rigorously you learned about logarithms in high school, it's possible that some students might think of these formulas as being bestowed upon them by the almighty math teacher, rather than really understanding where they come from. So the time has come to stop thinking of logarithms as mysterious things with laws and start becoming an expert in what a logarithm is and why those laws are actually true. So this is the explanation of where these laws come from. These cancellation laws can also be used to help us understand how to calculate the value of a logarithm, so let me show you that. If you're comfortable with logarithms, it's possible you can immediately identify the value of log base 10 of 100 is 2, but I want to make sure we're all able to understand why it's 2 using the proper logic and definitions. So let's pretend we don't know the answer is 2, and we'll indicate it as a question mark instead. The way you understand a logarithm is in terms of its relationship to exponential functions, because we know everything there is to know about exponential functions. So what you can do here is apply a base 10 exponential function to both sides. So on the left side, the cancellation law would apply, leaving us with just 100 on that side. Well, on the right side, this just reads as 10 to the power of question mark. So now what we're really asking is 10 to what power equals 100? But based on our knowledge of exponents, we know that 10 to the power of 2 is 100. So 2 must be the value of our question mark, and therefore it's also the value of our logarithm. So that's kind of the logical explanation of why that is. Now, phrasing this logarithm as 10 to what power equals 100 is probably how you're already used to thinking of this, so this probably doesn't feel new to you. But what might be new is the developing of a proper understanding of why the logarithm can be thought of in that way. So from this point forward, it's important that you're able to think about logarithms logically like this, rather than as a set of rules and tricks that your teacher gave you. We should also be aware of what the graph of a logarithm looks like. But as an inverse function, we know that the graph of a logarithm is just a reflection of the graph of an exponential. What you see here is the inverse of an exponential growth graph. So this is what a logarithm looks like when a is bigger than 1. And when a is less than 1, it looks like this instead. Again, it's important that you know these graphs or have them available on a formula sheet, especially for later on when we start calculating limits. There's a few more laws of logarithms that you should be familiar with. First of all, there's this law that when the input of a logarithm contains two factors which are multiplied, then the logarithm can apply to each factor separately, provided we add the results. To put it in an informal way, you could say that logarithms can turn multiplication into addition. In a similar fashion, we know logarithms can turn division into subtraction, and they can turn exponents into coefficients. More specifically, we know that any exponent attached to the input can be brought down in front of our logarithm like so. And finally, anytime you have a log with base a, you can always change it to a logarithm with a different base, say base b, provided that you divide by the log of the original base, which in this case would be the log of a. For future reference, this last law is called the base change formula. So we have all these laws that you've seen before, but where do these laws come from? Again, it's time to understand logarithms logically rather than as a bag of tricks. So let's see if we can actually prove the equality shown at the top of the screen and understand where it comes from. Actually, every single thing we know about logarithms is a consequence of something we know about exponentials. So here I've written down a familiar law of exponents, which says that exponential functions can turn addition into multiplication. So it should come as no surprise that logarithms, being the inverse function, should do the exact opposite. If exponentials can turn addition into multiplication, then logarithms should be able to turn multiplication into addition. But so far, that is just intuition talking. So let's form a more convincing argument by making an actual comparison between these quantities. But before I make that comparison, I'm going to apply a base a exponential to each of these. If these expressions are equal after applying this exponential, then they also must have been equal before applying it. So if the two expressions we see now end up producing the same result, then that would be enough to prove this law. Notice that the cancellation law can be applied directly to the expression on the left, so this simplifies pretty nicely to just xy. For the expression on the right, we can apply this property of exponents. And after doing that, the cancellation law can apply for the first factor, leaving us with just an x, but it also applies to the second factor, leaving us with just a y there. So we see both of these expressions give us a result of x times y, showing that they're equal, and that completes the proof. The proof of all the other laws is very similar, so I'll leave it to you to check those details for yourself. Now that we understand where these laws come from, let's make sure we're still good at actually using them in practice. So pause and see if you're able to solve this equation on your own, and when you're ready, let's continue. When your equation contains logarithms like this, my first suggestion would typically be that you gather all your logarithms on one side. So let's subtract this term over to the left-hand side, where now we see two logarithms being subtracted with the same base. So you might be tempted to use the subtraction law. But currently, this coefficient of 1/2 is preventing us from doing that. That's no problem though. This coefficient can be treated as an exponent of the input, just bring it up using another one of our laws. So that leaves us with this result. And now since the two logarithms on the left side are being subtracted, we can now combine them under a single logarithm by dividing the inputs. At the end of the day, our goal here should be to cancel out the logarithm since that's what contains all of our x's that we want to solve for. So then you should ask, how do we cancel out a base 2 logarithm? Well, that's done by applying a base 2 exponential. The inverse function is how you cancel it out. So just make sure you do that to both sides. Now a cancellation law can be applied on the left side, so our logarithm is gone there, and on the right side, 2 to the 3 simplifies to a value of 8. At this stage, all of our logarithms are gone, so I'm just going to say etc. and leave it to you to figure out the rest of this with a bit of high school algebra. As a final note, I'll remind you that you should always check for extraneous solutions after applying log laws, because sometimes the domain gets changed along the way when you do this. So hopefully this crash course in exponentials and logarithms was a good reminder of the basics, but for now that's all, and we'll continue this conversation in the next video.